So here's an example where we want to compute a double integral over a general region, meaning it's not a rectangle. And we would like to take actually maybe the less traveled path, meaning normally here you would go with vertical integration first, but we would like to go with horizontal integration just for the sake of the example. So in particular, let's see what the setup is. So the general setup for a situation like this is that we have the graphs of two functions. These are functions of y rather than functions of x. So this is x is equal to g1 of y. This is x equals g2 of y. We're going from a point C to a point D vertically. And that gives rise to this domain D, which can be described in terms of coordinates as all the x and y's, so that x is between g1 of y and g2 of y, and y is between C and D. And when we say that we want to move horizontally first, that will be over variable endpoints of integration. So this endpoint is precisely, so if we call this y, then this is g1 of y, and this is g2 of y, and it changes with each y. And when we say that we want to compute the integral of a function f of xy, which of course the function itself doesn't play any role in writing the iterated integral, this will be done as follows. So we integrate horizontally first, going from g1 of y to g2 of y, and then eventually we integrate over the vertical range from C to D. And that's exactly what we would like to implement here. And again, it's easier to go vertically first for the given example, but we would like to do it so as to stress that it's doable both ways. And it will give us some interesting limits and a more interesting integral. So again, this is a choice just for the sake of the example. So how do we describe the specific domain D that we're given, meaning this domain right here? So it consists of all the x and y's, such that y is between, so I'm sorry, x. We're doing horizontal integration first. So if I want to know where x is lies, I will need my left boundary, which is this one, and I will need to express it in terms of x. I'm sorry, in terms of y. So solve for x. So this is x is equal to square root of y. And the right boundary is the line x equals 1. So that means that I will have square root of y and 1. And y is simply between 0 and 1. And now I have everything that I need. So our integral over d of x y cubed dA will be written as an iterated integral from square root of y to 1 xy cubed dx. That's the important part. And then dy from 0 to 1. And now we're going to do our integration first with respect to x. So y is kept constant. So we get x squared over 2 times y cubed. And if we want to stress the fact, I mean, normally I would just put square root of y and 1. But if we want to stress the fact that we're substituting for x, we can put it like this, and with the x's, and then from 0 to 1 dy. So what do we get? We're going to get y cubed over 2. That's when we plug in x equals 1. And x squared, and if we plug in square root of y into x squared, then we simply get y. So that would be minus y to the 4th over 2 dy. And now, of course, this is a very simple integral. This will be the antiderivative of y to the 3rd over 2 will be y to the 4th over 8. And the antiderivative of y to the 4th over 2 will be y to the 5th over 10. And we want to go from 0 to 1, which means we're going to subtract 1/10 from 1 8. And of course, if we want to find a nice fraction as our answer here, we need to take the least common multiple, which is 40. And we will write this as 5 over 40 minus 4 over 40. And this will give us 1 over 40 as our final answer. And that's it. Thanks for watching.